Hello and welcome to ITN Module 7, Ethernet Switching, which is one of the most common LAN technologies, one reason for which is the high bandwidth capability of Ethernet. This module will teach you how to dissect the fields of an Ethernet frame, as well as make you familiar with Ethernet MAC addresses, how a switch uses them to forward frames, and Layer 2 switch port setting. This module starts with a discussion of Ethernet technology, including an explanation of MAC sublayer and the Ethernet frame fields. Ethernet is a wired LAN technology which uses twisted pair, fiber optic, and coaxial network media. Ethernet functions in two layers of the OSI model, the data link layer and the physical layer. The IEEE 802.2 standard defines Ethernet at the logical link control or LLC sublayer of the data link layer, and the IEEE 802.3 specification defines Ethernet at the media access control or MAC sublayer and the physical layer. Ethernet supports data bandwidths ranging from 10 megabits per second to 100 gigabits per second. To quickly review the functions of the LLC and MAC sublayers, the IEEE 802.2 LLC sublayer interfaces between the upper and lower layers. The LLC layer's main job is to add information to the Layer 2 frame, whether the network protocol in use is IP version 4, IP version 6, or some other Layer 3 network protocol. The MAC sublayer of the data link layer is in the hardware and takes care of data encapsulation, data link layer addressing, and media access control, hence the name MAC sublayer. The IEEE 802.3 data encapsulation that happens at the MAC sublayer is really the building of the Ethernet frame structure. Part of that is the Ethernet source and destination MAC address necessary to deliver the Ethernet frame from one Ethernet NIC to another Ethernet NIC on the same LAN segment. Another integral part of the Ethernet frame structure is the frame check sequence or FCS trailer used for detecting errors. In the figure, the IEEE 802.3 standard is further subdivided into a specification for each type of Ethernet media. For example, 802.3u defines fast Ethernet, which has 100 megabits per second bandwidth. 802.3z defines gigabit Ethernet, or Gig-E for short, over optical fiber. 802.3ab applies to Gig-E over copper, and 802.3ae applies to 10 gigabit Ethernet over optical fiber. Some important 802.3 rules to call out about Ethernet frames. They must be at least 64 bytes long, and no larger than 1518 bytes as measured from destination MAC address field through frame check sequence field or FCS field. The preamble field is not included in the frame size. Although it's beyond the scope of this course, maximum frame size can be extended through configuration as required. Dropped frames are usually caused by collisions or signal interference. Any frame less than 64 bytes long is called a collision fragment or a rent frame and is automatically thrown away by receivers. Frames carrying more than 1500 bytes of payload in the data field of the frame are called jumbo or baby giant frames and will be dropped by the receiver unless configured to process jumbo frames. The individual fields of an Ethernet frame are shown here. At the front of the frame is the 8 bytes long preamble and start frame delimiter or SFD field. The purpose of this field is to synchronize the sender and receiver and get the receiver's attention to get ready to receive the frame. After the preamble SFD field comes the 6 byte destination MAC address field that identifies which device the frame is for. This field is towards the front of the frame so that a receiving device doesn't have to read very far into the frame to tell if the frame is for them and whether or not to accept it. Directly after that is the 6 byte source MAC address field identifying the sender's hardware interface address. Towards the middle of the frame is the 2-byte tight length field, sometimes also called the ether type field, where the LLC layer provides a hexadecimal code identifying the upper layer network protocol being encapsulated inside the frame. An IP version 4 packet is coded hexadecimal 0800, and an IP version 6 packet has the hex value 86DD. Next comes the data field, normally 46 to 1500 bytes long, containing the encapsulated packet. If the packet is too small, this field can be padded with additional bits needed to increase the size of the frame to the required 64-byte minimum length. The last field in the Ethernet frame is the 4-byte frame check sequence, or FCS field, used for error detection using the cyclic redundancy check, or CRC, that the sender places in the FCS field before sending the frame. The receiver also performs a CRC of the frame, and if the results match, the frame is accepted. If the calculation doesn't match, it's assumed that the encapsulated data has been changed. For example, as a result of signal interference changing the bits that make up the message, so the receiver will drop the frame. Now it's time for a closer look at Ethernet MAC addresses. As a quick review, we've learned that IP version 4 network addresses use decimal, or base 10, and binary, or base 2 numbers, and that IP version 6 and Ethernet addresses use hexadecimal, or base 16 numbers, 0 to 9, and letters A to F. The Ethernet MAC address is 48 binary bits represented by 12 hexadecimal values. One 4-bit hex value for every 4 binary bits. A common binary grouping is 8 bits, also known as an octet, or 1 byte. The figure shows some of these alongside their decimal and hexadecimal equivalents. Notice the leading zeros used as placeholders in the hexadecimal 8-bit representation. For example, binary value 0001010 is shown in hexadecimal as 0A rather than just A. In documentation, hex numbers are often shown preceded by 0x to differentiate them from decimal numbers. Another way sometimes used is to add a 16 subscript, or uppercase H, directly following the hex value. As we've learned, Ethernet LANs are multi-access environments where every device is connected to shared media and where MAC addressing is used at layer 2, the data link layer, to identify the local physical source and destination NIC or interface. The figure demonstrates the 48-bit Ethernet MAC address expressed using 12 hex values and equivalent to 48 bits divided by 8 bits per byte equals a length of 6 bytes. To ensure that all MAC addresses are unique to a particular Ethernet device or interface, all Ethernet device vendors must register with the IEEE and obtain a unique 24-bit code known as the Organizationally Unique Identifier, or OUI. The vendor must follow a specific format when assigning a MAC address to a device or to the Ethernet interface on a network router or switch. As shown in the figure, the IEEE assigned OUI will be the first 6 hex values in the MAC address, and the remaining 6 hex values will be a unique value determined by the vendor. For example, the IEEE assigned Cisco the OUI of 00602F. So when addressing a new device or interface, 00602F would be the first 6 values that Cisco would configure the device. Cisco would assign a unique code, such as 3A07BC, for the vendor assigned portion, And the unique Ethernet MAC address would then be 00602F3A07BC. The MAC address, sometimes called a burned-in address, because it's permanently hard-coded into read-only memory, or ROM. When a device boots, its MAC address gets copied from ROM into RAM. When the device sends a message on an Ethernet network, that MAC address will be in the Ethernet frame as the source address. If a frame is destined for that device, its MAC address will be the destination address. The animation shows the frame forwarding process for a frame being sent from PC H1 to PC H3. The NIC hardware on H1 is the source address, and H3's NIC address is the destination. A NIC receives the Ethernet frame and checks to see if the destination MAC address matches the physical MAC address stored in RAM. If there is no match, the device doesn't need to view the rest of the frame and discards it. If the MAC is a match, the NIC passes the frame up to the upper OSI layers to be de-encapsulated and processed. What if a frame needs to go to more than one destination address? Then the frame destination address would be a multicast or broadcast address. Before we get into those, it's time to introduce the term unicast, which refers to the unique MAC address that was just discussed and is used when a frame is sent from a single sender to a single receiver or destination device. The animation demonstrates a unicast frame being processed. In this example, the source host requests a web page from the server at IP4 unicast address 192.168.1.200, which is the destination IP address in the IP packet header. Then, the corresponding destination MAC address must also be included in the Ethernet frame header. The IP address and the MAC address combined will deliver the data to that one host. In this example, both the source and destination addresses are unique unicast addresses. In fact, the source MAC address of a frame will always be a unicast or unique address. A couple of processes that we will learn about later are used if a device knows the IP version for address, but not the MAC address for a destination. It will use a process called Address Resolution Protocol, or ARP, to find out. For an IP version 6 address, the process is called Neighbor Discovery. In Ethernet, in addition to the unique unicast address, there are special MAC addresses called broadcast and multicast addresses, which are used to send a frame to more than one addressee. When a frame needs to be sent to and processed by every device on the Ethernet LAN, that is called a broadcast frame. The source MAC address of a broadcast frame will be the unique unicast source address of the sender, but instead of a unique unicast destination address, the broadcast frame will have a destination MAC address of all Fs in hexadecimal, which equates to 48 ones in binary. When an Ethernet switch receives a broadcast frame, it will flood the frame out all Ethernet switch ports except the incoming port. That is one major difference between switches and routers, because routers will not forward a broadcast frame. This is because Layer 3 routers are the boundary of the broadcast domain and will therefore not forward Layer 2 broadcast frames. At Layer 3, where the PDU is a packet rather than a frame, if a packet is intended for every device on a certain IP version 4 network, the packet encapsulated inside the frame will have all ones in the host portion of the network address. In this case, the host portion is 255, which is the decimal equivalent of 8 binary ones. This means that this inner packet is a broadcast packet, and all hosts on network or broadcast domain 192.168.1.0 will receive and process the packet. The animation demonstrates a broadcast frame where the destination MAC address and the destination IP address are both broadcast addresses. Source host H1 sends an IP version 4 broadcast packet destined for all devices on the LAN. The IP version 4 destination broadcast address 192.168.1.255. When H1's NIC encapsulates the broadcast packet inside of the Layer 2 Ethernet frame, H1 SNCC will set the destination MAC address to broadcast MAC address of all Fs in hexadecimal. An example of a protocol that uses Ethernet and IP version 4 broadcast addresses together is Dynamic Host Configuration Protocol, or DHCP, which is used to dynamically assign IP addresses to hosts on a network. What if a frame is intended for multiple but not all recipients on a LAN? In this case, an Ethernet multicast frame is used because it can be received and processed by a group of devices on an Ethernet LAN that are members of the same multicast group. A multicast frame destination address is different from a unique unicast destination address and different from a broadcast address of all Fs or 1s. A multicast frame will have a destination MAC address beginning with 01005E if the encapsulated packet is IP version 4, as is the case here. If the encapsulated packet is IP version 6, the multicast frame will have a destination MAC address beginning with 3333. A switch will flood a multicast frame out all Ethernet switch ports except the incoming port, unless the switch has been configured for multicast snooping. A router, on the other hand, will not forward a multicast frame unless specifically configured to route multicast packets. In the IP multicast packet encapsulated inside the multicast frame, the member devices of the multicast group will have a multicast group IP address within address range 224.0.0.0 to 239.255.255.255 for IP4, as shown here, or starting with FF00::/8 for IP version 6. Like unicast and broadcast frames, the source address of a multicast frame will always be a unicast address. The animation demonstrates that a multicast frame is being processed. Notice the multicast destination MAC address, which begins with 01005E, and the corresponding multicast destination IP version 4 address in the 224 network range are both multicast. The two devices who receive the frame but do not belong to the multicast group will simply discard the frame. Some uses of multicast addressing include IP routing and other network protocols. Another multicast example is a video application like IPTV, where there is a central server sending a continuous stream to multiple endpoints. Hopefully by now you understand Ethernet MAC addresses pretty well and are ready to move on to the subject of how an Ethernet switch uses MAC addresses to forward or discard frames to other devices on a network. We learned that a legacy hub would receive a frame on one port and simply repeat the same frame out all other ports. You can imagine what would happen if an Ethernet switch did the same thing. The network would quickly become congested and overloaded with traffic. There's no need to worry, because a Layer 2 Ethernet switch uses logic involving those Layer 2 MAC addresses to make calculated forwarding decisions. The switch is oblivious to the data portion of the frame and takes only the Layer 2 Ethernet MAC addresses into account when making forwarding decisions. Unlike those legacy Ethernet hubs repeating bits out all ports, an Ethernet switch has an internal MAC address table, which it uses to make a forwarding decision for each incoming frame. You might also hear the MAC address table referred to as a CAM, or Content Addressable Memory Table. In the figure, hosts A through D are connected to a Layer 2 Ethernet switch, which has just been powered up. Therefore, its internal MAC address table is empty because the switch hasn't yet learned the MAC addresses of the 4 attached PCs yet. For demonstration purposes, the MAC addresses have been shortened from 12 to 4 hexadecimal characters. After a switch is powered on, it will automatically build its MAC address table by learning the source MAC address frames it receives on a port. When the switch forwards frames, it searches for the destination MAC address in the MAC table. In short, source addresses are used for learning and destination addresses are used for forwarding. The switch is always learning, examining every incoming frame's source MAC address for new information, as well as noticing the port number that the frame entered through. If the switch sees a new source MAC address that isn't in its MAC table yet, the switch adds it to the table, accompanied by its incoming port number. When the switch sees a source MAC address that does already exist in the MAC table, the switch updates the refresh timer for that entry in the table. The default time that an Ethernet switch will hold a MAC address in the MAC table is usually 5 minutes. If there is an entry for the MAC address, but on a different port, the switch will create a new MAC address entry using the new incoming port number. In the figure, PCA sends an Ethernet frame to PCD. The switch examines the source address of the frame, sees that it is not in the MAC address table, then adds PCA's MAC address along with the incoming port number 1. That was an explanation of the MAC address learning process. Now look at the forwarding process used by the switch as it examines the frame destination MAC address. If the destination is a unicast address, the switch will search the MAC address table, and if it finds a match, it will forward the frame out the designated port. If the destination unicast MAC address isn't in the table, that's called an unknown unicast, and the switch will forward the frame out all ports except the incoming port. In the figure, the switch receives a frame from PCA destined for PCD's MAC address, and since the switch doesn't have PCD's destination MAC address in its table, the switch sends the frame out all ports except incoming port 1. That's called an unknown unicast. If the destination MAC address is a broadcast or a multicast frame, the switch will also flood the frame by default, unless configured otherwise. As the switch continues to receive frames from different devices, it is busy learning the source MAC address of every frame and populating the MAC address table with those source addresses and their corresponding ports. This knowledge is what will keep the switch from having to flood a frame, because of what we refer to as filtering. When the switch finds the destination MAC address in the table, the switch can filter the frame, forward it out a single port. In the previous figure, we saw the switch receive a frame from PCA for PCD, but the switch hadn't learned PCD's MAC address yet, so it had to flood the frame from PCA out all ports except the incoming port. PCB and PCC would have discarded their copies of the flooded frames as soon as they saw the destination address didn't match their NIC address. PCD, now in this figure, replies back to PCA. The switch sees PCD's source MAC address in the frame as it enters the switch on port 4. The switch adds PCD into the MAC address table associated with port 4. Next, the switch finds PCA's destination MAC address in the MAC address table, so it will filter, send the frame out port 1 only, rather than flooding. Next, PCA sends another frame to PCD. Looking at the source address, the switch sees that PCA's MAC address is already in the table. The switch resets the 5-minute refresh timer for PCA's entry in the table and then filters the frame, sending it out port 4 only. Now that we've covered how switches make forwarding decisions using their MAC address tables, it's time to look at 2 frame forwarding methods used on Cisco switches depending on the situation. The 2 main forwarding methods switches use when switching frames between network ports are called store and forward switching and cut-through switching. The store and forward switching method receives the whole frame and then computes the cyclic redundancy check, or CRC, using a math formula based on bit count to see if the frame has an error. If the CRC is good, the switch then does its normal procedure, looks up the destination address and forwards the frame out the correct port. The cut-through switching method, on the other hand, forwards the frame before the switch has finished receiving all of it. Of course, at a minimum, the switch has to at least read the destination of the frame before it can forward it. One strong advantage of store and forward switching is the CRC check the switch does to see if a frame has errors before forwarding it, and if it does detect an error in a frame, the switch discards it. Discarding corrupted frames reduces the bandwidth consumed by corrupt data. Store and forward switching is essential for quality of service analysis on networks which converge data with voice traffic, where frame classification is necessary for traffic prioritization of voice over IP data streams over web browsing traffic. In the animation, the layer 2 switch is using store and forward switching because it receives the entire frame from the source, calculates the CRC, compares the CRC result it got with the one calculated by the sender, determines the frame is error-free since they match, checks the MAC address table for the destination address, then forwards the frame out the correct port. Cut-through switching starts forwarding the frame before the entire frame is received. The switch buffers in memory only enough of the frame to read the destination MAC address. As you might remember, the destination MAC address is in the first 6 bytes of the frame following the preamble. The figure is demonstrating cut-through switching. The switch looks up the destination in its switching table to find the outgoing port and forwards the frame on its way without doing any error checking. Within cut-through switching, there are 2 subtypes, fast-forward switching and fragment-free switching. Of the 2 subtypes, fast-forward switching is the most common. Fast-forward switching has the lowest latency, or delay, because it immediately forwards a frame as soon as it reads the destination address. Latency is measured from the first bit received to the first bit transmitted. Because fast-forward switching starts forwarding before the whole frame has been received, frames with errors are forwarded. This doesn't happen often, and if it does, the destination NIC will see the error and discard the faulty frame. The fragment-free subtype of cut-through switching stores the first 64 bytes of the frame before forwarding. Because most network errors and collisions happen during the first 64 bytes. This provides a benefit over fast-forward switching by error checking the first 64 bytes of the frame to make sure a collision hasn't occurred before forwarding the frame. Fragment-free switching provides a happy medium between the high latency and high integrity of store and forward switching and the low latency and the reduced integrity of fast-forward switching. Some switches will perform cut-through switching on a per-port basis until a user-defined error threshold is reached and then automatically change to store and forward. When the error rate falls below the threshold, the port automatically changes back to cut-through switching. There are times when an Ethernet switch may need to buffer or store frames in memory before forwarding them. For example, if the destination port is busy because of congestion, the switch might buffer the frame until it can be forwarded. There are 2 methods of memory buffering, port-based memory and shared memory. Port-based memory is a buffering method which stores frames in queues, which are linked to certain ports. Once all the frames ahead of it in a queue have cleared, then a frame will be sent. With port-based memory, a busy destination port can cause a single frame to delay all the frames behind it from being transmitted. Shared memory is a buffering method which dynamically allocates buffer memory and keeps all frames in one memory buffer shared by all switch ports. Shared memory automatically links buffered frames to their destination port without changing queues. Shared memory buffering can store larger frames with potentially fewer dropped frames, which is helpful with asymmetric switching. Asymmetric switching uses different data rates on different ports, such as a server on a 10 gigabits per second switch port, which needs more bandwidth resources, versus PCs on 1 gigabit per second switch ports. A couple of basic settings on a switch are bandwidth and duplex. It is very important that duplex and bandwidth settings match at both ends of the connection. The 2 types of duplex settings used on an Ethernet network are full duplex, where both can send and receive simultaneously, and half duplex, where only one device can send at a time. Gigabit Ethernet ports operate only in full duplex. Auto negotiation, or auto for short, is the default on most Cisco switches and Ethernet NICs. Auto negotiation lets two devices automatically negotiate the best speed and duplex capabilities possible. Full duplex is negotiated only if both devices have the capability. In the figure, the Ethernet NIC for PCA can operate in full or half duplex and in 10 megabits per second or 100 megabits per second. The switch port PCA is connected to can support full or half duplex and speeds of 10, 100, or 1000 megabits per second. 1000 megabits per second is the same as 1 gigabit per second. If both devices are configured for auto negotiation, the result will be the highest common denominator, which is full duplex and 100 megabits per second. On 10 megabit per second and 100 megabit per second Ethernet links, duplex mismatch is a common cause of connection problems. As shown in the figure, S2's port on the link is operating at half duplex mode, while S1's port is set to full duplex mode. S1 is continually sending frames as per full duplex behavior, while S1 is experiencing collisions. One cause of duplex mismatch is one or both ports on the link being reset and the auto negotiation process being unsuccessful. Duplex mismatch can also happen when users reconfigure one side of a link and forget to change the other side. Both sides of a link should have auto negotiation on, or both sides should have it off, as long as it's the same on both sides. The best practice in this example is to configure both Ethernet switch ports as full duplex. Historically, connections between devices on a network required either a crossover or straight-through cable, depending on the type of devices being connected. The figure shows the correct cable type for interconnecting switch to switch, switch to router, switch to host, or router to host devices. A crossover cable when connecting like devices, and a straight-through cable for connecting dissimilar devices. A direct connection between a router and a host requires a crossover connection. Between a PC and a switch, a straight-through cable, because they're not the same. These two devices are different. Router to switch requires a straight-through cable. And these are the same, so they require a crossover cable to switches. Nowadays, most switches support the Automatic Medium Dependent Interface Crossover, or Auto MDIX feature. With MDIX enabled, the switch automatically detects the type of cable attached to the port and configures the interfaces accordingly. Therefore, you can use either a crossover or a straight-through cable for connections to a copper 10, 100, 1000 meg port on the switch, regardless of the type of device on the other end of the connection. The Auto MDIX feature is enabled by default on switches running Cisco iOS release 12.2.18 SE or later. It's a good practice, though, to use the correct cable type. That was a lot of information about Ethernet switching, and hopefully you are ready to take the module quiz.